I would like to remember that today's evening we have the opening ceremony. During this ceremony, Professor Rui Togero will talk about Marcos and some of his works. Our next speaker is Gorodski from USP. He's going to speak on homogeneous isoparametric submanifolds of type AN in Hilbert spaces.
Thank you. So, I'd like to thank the organizers for these invitations. I want to congratulate Marcos on this occasion. And what I'm going to talk today is joint work with Ernst Heinze from the University of Augsburg. And I think he's here today. And some of the ideas can also be traced back to a PhD thesis of a student of him, Kerstin Weiner. So I'm going to start with the definition of isoparametric submanifold in Euclidean space. So M is called isoparametric. There are two conditions. If the normal bundle is flat, and the eigenvalues of the shape operators along parallel normal vector fields are constant for any codimension. And also, of course, Euclidean space could be replaced by any space form. So in the hypersurface case, this simply means that M has constant principal curvatures. And this concept goes back to Cartan, who did a lot of work on that, and even earlier. It seems that the study of such submanifolds in R3 was motivated by some problems in optics and something like that. But in higher codimension, it's more recent. It was introduced in the early 80s independently by Edgar Harley, Carter and West, and then Thurn. And Thurn did extensive work on that. And she also worked in infinite dimensions. So she introduced this category of proper Fredholm submanifolds. I'm going to say, well, it essentially means that the codimension is finite and the shape operators are compact. So this is a technical condition to be able to work. And it's interesting to remark that there exist homogeneous and inhomogeneous examples. So, of course, in this talk, we are interested to discuss the homogeneous examples, but there are also inhomogeneous ones. Okay, so about homogeneity, so homogeneous isoparametric submanifolds are very, very much related to polar actions. So I should explain now what are polar actions. So we take a smooth proper isometric action of a compact of a Lie group on a complete Riemannian manifold, and it's called polar if there exists a submanifold sigma meeting all the orbits and meeting them always orthogonally. So sigma is called a section. And it's very easy to see that a section must be totally geodesic. So this definition makes sense in the linear and nonlinear case, but let's see some examples in the linear case. So the basic example is the SON action, Rn is polar. Any line through the origin is a section. So the name polar, of course, comes from this example. And then we have the next example. It's also very basic, SON conjugation of symmetric matrices. In this case, the section is given by diagonal matrices. And finally, these two examples can be generalized. If you take any Riemannian symmetric space, Cartan decomposition, K plus P, then the joint action of K and P is polar. The section is given by a maximal abelian subspace of P. Also, in infinite dimensions, we can use the same definition, but we have to work in the category of proper Fredholm actions by affine isometries on Hilbert spaces. Okay. So Fredholm means that the group acting at a point we get the orbit. And the differential of this map is a linear Fredholm map. So what's the relation then? So the relation is that if you take any principal orbit of a polar representation, then observe that this gives an isoparametric submanifold. Sorry. So since this is such an important relation, let's spend 2 minutes proving this. It's a very simple argument. So suppose we take a principal orbit of a polar representation on a Euclidean space. So the first remark is that the isotropy group at P acts trivially on the normal space. So this is general for principal orbits. Therefore, any vector normal at P can be extended using the group to an equivariant normal vector field along the orbit. And then we take sigma to be the normal space at P. So by assumption, the action is polar. So sigma is a section, so it meets, for instance, it meets the orbit through P plus V orthogonally. So if you take a one-parameter group in G, we have this orthogonality here. And then we also know that at P, this curve is orthogonal to sigma. Therefore, we see that this equivariant vector field has no normal components. And so we have proved that equivariant normal vector fields are parallel with respect to the normal connection. So since these are globally defined and, of course, have constant, the shape operators, the corresponding shape operators have constant eigenvalues, this proves that the orbit is isoparametric. So it's a very simple argument. So we have this implication, and there's also a theorem by Torbergson. So the dotted line means there is some restriction here. So the restriction is that the codimension must be different from 2. If the codimension in the Euclidean space is equal to 2, then there are examples of inhomogeneous isoparametric submanifolds. So in codimensions different from 2, we have this reverse implication. And we also said that we can get polar representations from isotropy representation of symmetric spaces. And finally, we have a theorem by Dadok. He classified polar representations and showed that such representations have the same orbits as an isotropy representation of a symmetric space. So we have a complete description here in finite dimensions. And so the next thing, we'd like to have similar description in infinite dimensions, right? So in fact, most of the work is already done. So we can explain this now. So Tern, in another paper, she introduced polar actions, isoparametric submanifolds. Essentially, the same proof shows that there is this relation between them. And also, Torbergson's theorem was, well, there was another proof later by Carlos Olmos. And after that, Heinz Liu extended the theorem to infinite dimensions. And the proof of Heinz Liu is also valid for finite dimensions. But in the infinite dimensional case, the dotted line means that the codimension here must be different from 1. So then we have this reverse implication. And then we'd like to have also some relation to symmetric spaces in infinite dimensions, but this is a little bit more complicated, so we have to break this into some pieces. So first recall these PGH actions on Hilbert spaces, which were introduced by Tern. So they give examples of polar actions. I'm going to explain. Sorry? I'm sorry, yeah. Yeah. Can I do something about this? Turn the light, maybe? Here? No. PGH action on Hilbert spaces. Okay. Is it better now? Sorry for that. So these are PGH actions on Hilbert spaces, a class of examples of polar actions on Hilbert spaces. I'm going to explain what they are in a moment. Yeah, this is going to be... Yeah, interesting. And Turn also showed that there is a bijection between these PGH actions and some hyperpolar actions on compactly groups with biinvariant metrics. Of course, biinvariant metric on the compactly group is not flat, and sections are totally geodesic. So in Euclidean space, sections are automatically flat, but in a big group, they're not necessarily flat. So hyperpolar means that we require the section to be flat. Okay? So hyperpolar means polar with flat sections. And so there is a bijection between these two classes. And in another paper by 4 authors, Heinze, Palais, Tern, and Torbergson, they described examples of such actions. So I don't have time to get into details. So these are sigma actions and Hermann actions. And finally, in this paper, they showed how to construct involutions of affine Kac-Moody groups, giving rise to symmetric spaces from these actions. So this is the relation to symmetric spaces. Then we have all these arrows. And the point is if we take the isotopic representation of such a symmetric space, then it is not automatically flat, but because the metric is Lorentzian there, so we have to restrict to a codimension 2 submanifold. And then after completing the metric, the action that we get there is equivalent to this PGH action. So this is the relation. And Andreas Kouros, in his PhD thesis, classified hyperpolar actions on compactly groups. And the dotted line means that the codimension, the cohomogeneity must be different from 1. So then there's a reverse implication. And finally, there's a recent paper by Heinze. He developed a new classification of involutions of affine Kac-Moody groups, which puts in evidence the relation to these classes of hyperpolar actions. So this is almost complete description, except for this arrow, of course, and then that's why we are studying this problem now. So let me explain now the PGH actions, what they are. So we start G with compact semi-simple group, and then we put a biinvariant metric on G, and then P of G is the space of paths from the unit interval into G of class H1. So it means Sobolev class H1. And then P of G has a natural structure of a Hilbert group by using pointwise multiplication. And so we have this group now. We construct the Hilbert space. The Hilbert space is going to be L2 paths into the Lie algebra of G. And then we take the trivial principal bundle, meaning just this trivial. So this is really a fancy way of describing those actions. Then P of G acts by gauge transformations because V can be viewed as a space of L2 connections. I mean, if you take a one form, omega, here, with values on the Lie algebra, Then, of course, this is a trivial bundle. We have a global section. You can pull back the one form. And since this one-dimensional, this is really a map from the interval into the Lie algebra. So we are considering connections of class L2. And then P of G is the gauge group. It acts by gauge transformations. So G, U, G minus 1 is a joint action. And then G prime, the derivative, we get tangent vector to the Lie group. We pull back by right translation to the identity. We get an element in the Lie algebra. So it's easy to see. It's a very simple computation. This action is transitive. But then we are going to restrict this action to a smaller subgroup. So H is going to be a closed subgroup of G cross G. For instance, could be the diagonal, for instance. So this G cross G should be viewed as the isometry group of G, left and right translation. So H acts on G by left and right translations. This action is isometric, of course. And then PG of H is the closed finite codimensional subgroup consisting of paths with endpoints in H. So this action, we restrict the action of PG to PG of H, and this action is isometric, smooth, proper, and Fredholm. And then we have a holonomy map. Of course, we have just one path in the base going from 0 to 1. We start at identity. Given a connection, we have parallel transport. We end up with an element of G. So this is a holonomy map. And it's a simple computation to see it's equivariant with respect to the gauge action upstairs. And then downstairs, we have H acting. And it's equivariant with respect to this epimorphism. So we just take the endpoints here. And the main result here of turn is that the action upstairs is polar, if and only if the action downstairs is hyperpolar, polar reflex sections. So this is the bijection we told about before. Okay. So these are the PGH actions. And so the main theorem we have proved recently, we still have to check some technical details maybe, but it's essentially proved. So consider a polar action of a Hilbert Lie group. So this is bold phase G to distinguish it from the other G. On an infinite dimensional Hilbert space, so then we know that the orbits, the principal orbits, are isoparametric. So they have a Dinking diagram. I'm going to talk more about that. But suppose that this Dinking diagram is of type A n tilde. And here we assume n at least 2. This means that the codimension is at least 2. So our theorem does not apply to hypersurfaces. Then GV has the same orbits as a PGH action. So in order to prove this theorem, it's enough to take a principal orbit of this group and to show that this orbit coincides with the orbit of an action of this type on the same space. Because then the other orbits are just parallel submanifolds. So we are done. So I'm going to talk more about that also. So it's natural to pose this conjecture. I mean, at least in the reducible case, the homogeneity bigger than 1. So we can remove this assumption of the Dinking diagram. So the main tool is this rigidity theorem. It's not difficult to prove. So if you take two isoparametric submanifolds, M and M prime in V, both homogeneous with respect to Hilbert Lie groups, G and G prime. And then we can, of course, use translations and rotations in the ambient space so that we get a point, a common point P, where tangent spaces coincide. But suppose they have the same codimension, for instance. Then we can do that. And then the assumption is that the second fundamental forms coincide at this point P, and also this operator gamma for M and M prime, they coincide also at the point P. I'm going to explain what is this. Then the conclusion is that they're equal. So that's what we do. I mean, we start with a given action, we take some principal orbit, and then we assume it's of type A n tilde, and well, essentially we have to show that these invariants are uniquely defined. And then you have uniqueness, but you already have the PGH action with these invariants, then they must be the same. So if I have time, I come back to the proof of this rigidity theorem at the end of the talk. But I think it's important now to discuss the geometry of isoparametric submanifolds. I mean, there is a lot of structure here, really. So by assumption, Hilbert spaces are separable, isoparametric submanifolds are proper Fredholm, which we recall. It means that they're finite codimensional and have compact shape operators. So then we have also the normal bond is flat. So the Ricci equation implies that the shape operators commute. So we have a commutative family of compact self-adjoint operators. Hence, there is a common eigenbundle decomposition. And here is the Hilbert direct sum. So we have closure. But I is an index set. So EI is called a curvature distribution. So the shape operator restricted to EI is, I mean, this is it's diagonalized by this decomposition. So there is a corresponding principal curvature. We can represent it by normal vector field, VI, using the Hilbert inner product. Then this is called the curvature normal, and it's easy to check. It's parallel in the normal connection. In particular, you can rewrite this equation like this. If you take vectors in curvature distributions EI, EJ, alpha is given by the inner product. In particular, if I is different from J, then this number is 0. Kodaz's equation implies that EI is totally geodesic in M, with umbilic leaves in V. So this means that it's integrable, and if the dimension is finite, then it's just a round sphere in Hilbert space with this radius. Well, if VI is different from 0, then we have this. And the only possible infinite multiplicity corresponds to the 0 eigenvalue. And then we have an affine subspace as leaf. So our submanifold is foliated in infinitely many ways. It's a very rigid and rich structure. And we make the convention that the 0 curvature normal corresponds to the 0 index. So what's the affine value group then? Well, start with M, isoparametric, take a parallel normal vector field, then we have this endpoint map along C. We easily compute the differential, so we get shape operator. And restricted to EI, we get this number. So what's the kernel? So exactly when C dot VI is 1. So of course this depends on C. But anyway, since the rank of pi is constant, its image is a parallel submanifold, possibly focal if this kernel is different from 0. And the focal set decomposes. These are just hyperplanes. So we get a union of affine hyperplanes in the affine normal space. So the group generated by reflections on the focal hyperplanes is the Coxeter group, one shows, and it's really an affine Weil group at P, but this dependence of P is not very serious, of course. And then we have an associated Dinkin diagram. The vertex corresponds to a set of generators for this group. And we can also mark the vertices with some integers, which are the dimensions of the corresponding curvature distributions. So for instance, A2 tilde, we have this diagram. The possible multiplicity is 1, 2, 4, 8, and this is So these lines are the focal lines. So P is our point P. These black dots are the intersections of M with this affine normal plane. These blue dots are also just focal points, a little bit more degenerated. And then in red, green, blue, yellow, I draw some shades of curvature sphere. So the curvature sphere really comes out from P and then meets again these affine normal planes at the antipodal points. So we have infinitely many curvature spheres. For instance, for this yellow one, this middle point here is the center. It's a focal point. And if we take the blue, green, and red together, they focalize at this blue point here. So, in fact, if we take any point here, for instance, we have just this yellow curvature sphere focalizing here. But if you take this blue point, then we have a larger submanifold focalizing here, which contains these three curvature spheres. So this is related to the concept of a slice. So what a slice? We have this focal map. A slice is just the level set of the some level set of the focal map. Okay, some fiber of the focal map. Focal map is a submersion. Any fiber is a slice. So any curvature sphere is a slice, but we have also bigger slice. If you take this point, the slice contains these three curvature spheres, for instance. So slices, so here, this picture, I mean, I draw some curvature normals. So they come in parallel families. And by the formula, I mean, this formula here, for the kernel of the focal map, we see that what focalizes is given by this relation here. So here we are taking this line. So what are the curvature normals lying in this line? These three ones. One from the blue family, one from the green, one from the red. So in this case, we have a finite dimensional rank 2 slice of type A2, which is contained in our manifold of type A2 tilde. We can generalize this notion of slice a little bit to include also cases like this. I mean, in this case, we cannot focalize because these lines contain 0 here also, and 0 never focalizes, of course. But we can also generalize a little bit the notion of slice and include submanifolds like this. In this case, we get a rank 1 slice. I mean, it means that rank 1 means it's a cohomogeneity 1 submanifold, isoparametric also, of infinite dimension, but codimension 1, not in V, but in a smaller, slightly smaller subspace. So we have these two kinds of slices. So the idea is to slice. We have this infinite dimensional isoparametric submanifold in the Hilbert space, and we want to take slices. So we have two kinds of slices, finite dimensional ones, infinite dimensional ones. So in this case, I mean, finite dimensional isoparametric submanifolds are classified, so we can use this classification to get information about our manifold. Here we get an infinite dimensional slice, but it's still very useful to consider those because they're going to be hypersurfaces in a subspace of V. So now I give a very rough, broad outline of the proof. So first, this observation. I mean, if we have fixed this point P, tangent space, this decomposition into curvature distributions is GP invariant, of course. The group is acting by isometries. And then we are going to apply representation theory because this group is, I mean, this isotopic group is compact. So we can apply classical representation theory of compactly groups. And then also the classification of finite dimensional isoparametric submanifolds. And then combine everything. And so this is so we start with a Dynkin diagram, in our case A and tilde. The first thing is to determine the possible multiplicities. So We do that by using slices. So we take finite dimensional slices in this case. So these are finite dimensional, they are classified. So we know what the multiplicities are in the finite dimensional case, so we can recover our multiplicities from those. Oops. And in fact, this step was already done by turn, but in the homogeneous case, we can refine a little bit the list of possible multiplicities. So the second fundamental form at P is also very easy. We have this formula. So if you fix the Dinkin diagram and the multiplicities we have, the second fundamental form at the point P, just this formula. I mean, the Dinkin diagram determines essentially these vectors up to homotopy and up to parallel translation, maybe. And the multiplicities give the dimensions of these spaces, so no problem here. And then we look at these representations for I different from 0. Why I different from 0? Because if I is equal to 0, then E0 is infinite dimensional in general. So it's more complicated. So we first look at the finite dimensional curvature distributions. And here we can apply representation theory. So we have slices again. So EI for our manifold is going to be EI for some slice, which is finite dimensional. So we have some information there. And then we have also a very useful theorem about isometries, which I'm going to explain in a moment, to recover not only the dimension of EI, but also the action. Because, of course, when we restrict the action to EI, we may get a kernel, ineffective kernels. So we lose some information. So we have to glue together information coming from different slices. And then we use this theorem for that. And finally, we have some more tools here. Then we have to determine gamma at the point P. And then this is really the most involved part of the proof. So I have to explain what are these tools here. So really, these tools are very general. I mean, they apply to general isoparametric submanifolds. And then, of course, in the case of A and tilde, we use them to get a complete description of gamma. Okay, so let me explain what is this theorem. I mean, so suppose V is an ambient isometry which leaves invariant our isoparametric submanifold and fixes the point P. And suppose phi star is the identity on the normal space and in some subspace like this of the tangent space, where I prime is a finite subset such that the corresponding reflections generate the affine Weyl group. So, for instance, in this case here, I prime would be just reflections along the three sides of this triangle, for instance. The reflections on here, here, and here already generate the whole Weyl group. So we have finite data there. I mean. And then if you know that phi star is the identity there, then it's the identity everywhere. So in particular, if you take any element in the isotopic group at P, and we look at the action on this EI, where I belongs to I prime, then this map is injective. So it's completely determined by its restriction to this finite dimensional subspace. So therefore, we can take these finite dimensional slices and recover the whole isotopic group using this theorem. So this is very important. And another thing I have to explain then is the map gamma, which is another invariant we are using here. So we take here, we fix some index I, we take this curvature sphere, it's a finite dimensional round curvature sphere. And then Ci is the center of this sphere. The center, Ci, we take the isotopic group at the center. So recall, this is a focal point. So it contains properly the isotopic group at P. So it's easy to see it acts transitively on this sphere, so it can take a reductive decomposition. And in fact, there's a canonical one. In most cases, maybe in all cases, including in particular A and tilde, there's a canonical decomposition like this. And then we have a correspondence between elements in the Lie algebra here and vectors in EI given by just the action of the Lie algebra. And this is a smooth action, of course. And then we have this decomposition, linear isomorphism. We have an inverse denoted by hat like this. And so this is, just representing the sphere, the center. Any vector in EI can be written V hat applied to P, where V hat is in MI. And then gamma is just the action of this vector on any tangent vector. And then, so this is the Lie algebra action, and then we take the tangential component. Of course, the action of the Lie algebra is just the differential of the action of the Lie group. So in particular, if we extend this vector y to an equivariant vector field along the one parameter corresponding to xi, then we have this equivariant vector field. And if we differentiate it in Hilbert space and then project back to our manifold, then we get exactly the Levi-Civita connection. So we can express this gamma in these two equivalent ways. So it's really given by the action of these isotopic groups at the centers of the curvature spheres. And so, but look that this is an algebraic sum. I mean, we have defined this not for a sum, but just for a single xi. So there's no closure here, and also E0 is left out. I mean, we don't need to include E0 here. So some properties, I mean, this comes from the connection, so it's easy to see it's Q-symmetric. And also, essentially, it's almost given by the up to EJ, they coincide, really. Because, well, if we project, I mean, this to EK, where K is different from J, we get a tensor. Therefore, it's easy to see that they coincide. Mode EJ. It's also easy to see it's equivariant with respect. This should be both phase G here. And this is more interesting. I mean, this formula here is gamma. It shows that gamma determines completely nabla alpha, the covariant derivative of the second fundamental form. But nabla alpha is a geometric object, and gamma involves the action of the group. So somehow gamma contains a little bit more information. For instance, if J is equal to K, then this is 0 and nabla alpha is 0. But this need not be 0. So it contains more information somehow. So how do we compute gamma? So remember, I mean, we know already alpha. If we show that gamma is completely determined, then we have essentially uniqueness, and then we have already PGH action, so it must be that, right? Well, in fact, what happens in the case of A and tilde, we have 4 different multiplicities, 1, 2, 4, 8. So we have to analyze case by case. In cases 2 and 4, we get 2 possible isotopic groups, in fact. And in cases 1 and 8, we get only 1. But then, after that, we show that gamma is completely determined. So, and then we have the corresponding examples of PGH actions with those invariants. So it works very well in the case of A and tilde. So the basic observation here is that this map, if you look at gamma as a linear map from the tensor product, then it is equivariant with respect to GP. I and J here are different from 0, so EI and J are finite dimensional. So then we can decompose this tensor product into irreducible components, and can use true lemma on each one of them. Then gamma either kills a component or maps it onto an isomorphic representation. So another remark is that by definition, gamma of xi is given essentially by the action of this group. So we can also apply representation theory to this larger group and compare it with the smaller group. So this imposes lots of restrictions. And finally, I want to mention this standard computation, this formula, this complicated formula for gamma. There are some hypotheses on these vectors, indices, and so on. These Cij, M, and so on are constants, which we can compute. And this imposes lots of restrictions on gamma. And this formula essentially comes from the Gauss formula. I mean, really, the Gauss equation. I mean, gamma is skew-symmetric, right? So if we move this here, and then we can see the curvature appearing. And so this is essentially the Gauss equation. And then we take very many special cases of this equation, and we get many relations. I mean, it's a little bit technical. There are many computations, but everything is nice, and gamma is completely determined. So more specifically, we can say a little bit more here. So this map is equivariant, GP equivariant, but if I and J are such that Vi and Vj are parallel, I mean, they belong to the same family of parallel curvature normals, then, no, sorry, if they are not parallel, then the image of this map lies in EK, where K is different from 0, and EI, J, K lie in a finite dimensional rank 2 slice, similar to that picture that we had before. So in this case, everything is known up to isometry. Of course, this up to isometry is very tricky because we have infinitely many isometries like that, and we have to make sure we can choose them compatibly and so on. So, I mean, we have to choose bases for these curvatures, some canonical basis for these spaces, and in a compatible way, and then we can write down maybe the matrix of this map with respect to these bases, and so on. And we have also this other case. I mean, if they are parallel, then at least in this case of A and tilde, the image lies inside E0. So this is the case where we talked about before about the infinite dimensional rank 1 slice. So in this case, the image lies in E0. And then we have property P. Property P says essentially that, I mean, the image of gamma, the image of this map, if we take for every I and j different from 0 in the closure, then it equals E0. So then we can understand what happens in E0. E0 is infinite dimensional, but then we have this decomposition, and we understand what happens there. And then we have formulas for gamma, and we can understand what gamma does there too. So essentially, this is how we compute gamma. So since I have some time, I'm going to go back to the rigidity theorem to show that the proof is not difficult. So recall that we have two isoparametric submanifolds with the same codimension, both homogeneous, possibly with respect to different groups. And then we use translations and rotations to get a common point where the tangent spaces are common. So assume that the second fundamental forms also coincide and the gammas coincide. Then we're going to prove M is equal to M prime. So first thing, since the second fundamental forms coincide, then we know that the curvature spheres, at least at this point, P coincide. So in particular, we have correspondence between the set of indices of curvature spheres. I and I prime correspond. Fix such a curvature sphere at the point P, and a different point Q lying here. So we claim that the tangent spaces at the point Q, we have the exactly the same conditions that we had before for the point P, we have also at the point Q. This is our claim. And then essentially, we see that we'll finish the proof with this. So note that alpha and gamma are equivariant, but alpha prime and gamma prime are also equivariant, but with respect to different groups. So this is the point here, really, different groups. I mean, if we have the same element mapping P to Q, then we would be done, really. We have different groups. But anyway, we can find, we have those reductive complements. In each case, we can find those vectors such that at the point P, they give the same vector, xi, and such that if you exponentiate, yeah, Q lies in this curvature sphere. So we have a geodesic arc coming from P to Q. And then we have a one-parameter group in G, one-parameter group in G prime, mapping P to Q. Now we use the assumption at P, gamma and gamma prime coincide, alpha and alpha prime coincide. So, I mean, if you write down what this means, really, it means that xi hat and applied to V and xi prime hat applied to V are equal for any element in the Hilbert space. I mean, this is equivalent to essentially to these conditions here, and also using that equivariant normal vector fields are parallel. So it's just writing down what this means. In particular, if you exponentiate this relation, we get the corresponding elements in the groups G and G prime. They coincide as isometries of V. So the claim is proved. So tangent spaces alpha and gamma coincide also at Q. Now we use a result of Heinz-Liu, which says that the set of points of M or M prime that can be reached from P by following geodesic arcs and curvature spheres is dense. So you can proceed by induction, and we are done. So I'm going to stop here.
Any questions, remarks?
I'd like to know about relations between the study of like infinite-dimensional polar actions and like finite-dimensional polar actions or finite-dimensional geometry.
Well, you mean what kind of relation? I mean,
Some like application of this.
yeah, well, in general, it goes the other way, I think, right? I mean, we have this classification in finite dimensions, and we use this to understand what happens in infinite dimensions, right? But then the only known examples so far are the PGH actions, essentially. Well, maybe for homogeneity 1, there may be some other examples, maybe. But most of the examples are really PGH actions. And you see that we have this holonomy map relating. So we are really taking this finite dimensional action and unfolding it into infinite dimension. And then you have infinitely many, countably many copies of this finite dimensional situation glued together. It's a very complicated and rich structure, but infinitely many copies of this finite dimension. So essentially, for infinite dimensions, there are not many more examples, maybe. It's not clear. But at least for homogeneity bigger than 1. And homogeneity 1, maybe there are more examples, but I don't know very well. But the other way around, I don't know. I mean, you mean applications? Well, there are some relations, in fact. Yeah, right, because, I mean, in finite dimensions, sometimes you have a nonlinear problem. So you can lift it to Hilbert space, and you linearize it. Even if it's infinite dimensional, it's linear, so you can sometimes solve it in infinite dimensions. And then sometimes you can project down the solution. And this has been done in the literature in some instances for variationally complete actions, Todd submanifolds. I think there are some arguments like that too.
Any more questions? So let's thank Claudia again.
Mm-hmm.